Welcome to a lesson on double integrals and volume. This limit definition for volume should look very familiar to what we saw in Calc 1 for the limit definition of area. However, for volume, we're going to be summing the volume of rectangular prisms or boxes. To determine the volume of each of these boxes, we're going to determine the area of the base and then multiply it by the height. If we take a look at just one box, the area of the base, delta A, would be determined by multiplying delta x times delta y. Once we have the area of the base, we pick a point xy in this region, plug it into the function, and this gives us the height of the box. So the area of this base times the height of the box gives us the volume of each of these boxes. And of course, as we know from Calc 1, if we approximate the volume under this surface with more and more boxes, we will approach the volume underneath the surface. So this infinite sum here represents the area of those boxes. Again, this is the area of the base, this would be the height, and as a number of boxes approaches infinity, we're approaching the volume under the surface. And this is defined by the double integral over the specified region in the xy plane of f of xy. And notice here it's showing we're differentiating with respect to a. Well, differential a can be written as dx dy or dy dx, because either way it represents the area of the base of each box. So what I mean by that is, here's the form of a double integral that we normally see, where R is a region defined by x and y. So first we need to decide whether we want to integrate with respect to x first and then y, or with respect to y first and then x. We can use either order, but of course it will change how we arrange our limits of integration. Let's take a look at some examples. Here we want to determine the volume of the given surface on the closed interval from 0 to 2 for x and the closed interval from 0 to 3 for y. So looking at the xy plane, this would be our region of integration. And we also need to make sure that this is in the form of f of xy. So let's go ahead and rewrite this. F of xy would be equal to 12 minus x squared minus 1/2 y squared. Now we need to decide whether we want to integrate with respect to x first or with respect to y. Let's go ahead and set this up where we integrate with respect to x first and then y. Again, we'll first integrate with respect to x and then with respect to y. So the limits of integration for x will be from 0 to 2, and for y it'll be from 0 to 3. So we'll first integrate with respect to x, treating y as a constant. So we'll have 12x minus x to the third over 3 minus 1/2 y squared x. Remember, y is a constant. We'll evaluate this at the limits of integration, and then we'll integrate with respect to y. And because we integrate with respect to x, we're going to replace x with 2 and 0. So when x is 2, this will be 24 minus 8/3 minus y squared. And when x is 0, each of these terms will be 0. Let's go ahead and finish this on the next slide. Let's go ahead and subtract these. We're going to have 64/3 minus y squared. And now we'll integrate with respect to y. We're going to have 64/3 y minus y to the third over 3. Now we'll replace y with 3. And then y with 0, and these will both be 0. So we're going to have 64 here, and this will be minus 9, which gives us 55. And since this represents the volume under that surface on the given region, this would be cubic units. Let's take a look at this in 3 dimensions. So in yellow we see the surface, and then these planes represent the region. So the amount of volume under the yellow surface above the xy plane would be 55 cubic units. Let's go and take a look at another example. There are several ways to define a region. If it's defined like this, we always assume that this interval is for x and this interval is for y. So if x is on the closed interval from 1 to 2 and y is on the closed interval from 0 to 3, our region of integration in the xy plane would be this region here. It's a good habit to sketch this because if it's not a rectangular region, the sketch here becomes very important. So in this graph, we see the surface graphed over this region, so we're trying to find the volume under this surface. Let's go to integrate with respect to y first this time. F of xy is xy squared, and we'll integrate with respect to y first and then x. So the interval for y is from 0 to 3. The interval for x is from 1 to 2. So we'll first integrate with respect to y. Treating x as a constant, we'll have xy to the third over 3. We evaluate this in our limits of integration, and then integrate with respect to x. And again, because we integrate with respect to y first, we're replacing y with 3 and y with 0. So when y is 3, this is going to end up being 9x. And then when y is 0, it'll be 0. So now we integrate with respect to x. That'll give us 9 times x squared over 2. So when x is 2, we're going to have 4 divided by 2, that's 2 times 9, that's 18. And then when x is 1, we'll have 9 times 1 half, or 9 halves. Well, 18 minus 9 halves, that'd be 36 halves minus 9 halves. That'll give us 27 halves. And again, this represents the volume under the surface in this region in the xy plane. Let's take a look at this in 3D as well. In yellow, we see the surface, and the region for this problem is this region in here. So we're looking for the volume under the yellow surface in this region, looking for this volume in here. Let's take a look at one more example. On this example, our region is the closed interval from 0 to 1 for x, and from 0 to pi over 2 for y. So again, we have a rectangular region that looks something like this. So this would be our region of integration. Now sometimes when setting up a double integral, the order of integration does matter based upon our integrand. Meaning for this one, it's going to be much easier if we integrate with respect to y first and then x, because if we integrate with respect to y first, we can treat this x here as a constant. Otherwise, it would be much more challenging to integrate. So if we integrate with respect to y first, the limits of integration for y would be from 0 to pi over 2, and for x it'll be from 0 to 1. Now even though we're treating x as a constant, we do still have to perform u substitution because we have the cosine of x times y. So if we let u equal xy, differential u with respect to y would be x dy. And this is actually good news because the integrand does contain x dy. So this just becomes cosine u, and the antiderivative of cosine u is sine u. So we'll have sine u is actually xy. Of course, we have to evaluate this at our limits of integration, and then integrate with respects to x. And because we integrate with respects to y, we're replacing y with pi over 2 and 0. So when y is pi over 2, we'll have sine pi x over 2. And then when y is 0, we'll have the sine of 0, which is just 0. Let's go ahead and finish this on the next slide. We do have to perform u substitution again. U is going to be pi x over 2. So differential u is going to be pi over 2 dx, which means dx is equal to 2 over pi du. So we'll have an extra factor of 2 divided by pi. And the antiderivative of sine u is going to be negative cosine u, so we'll have negative cosine pi x over 2. Let's see what this gives us. When x is equal to 1, we have negative cosine of pi over 2. Well, cosine pi over 2 is 0. And then the cosine of 0 would be 1, but notice we have a negative sign there, so it's negative 1. So we end up having pi over 2 times positive 1, which is just pi over 2. So this would be the volume under this surface over this region in the xy plane. That'll do it for this video.